Have you ever looked up at the night sky and wondered what's really out there? The universe is vast, mysterious, and full of unanswered questions. But there's one cosmic secret that has puzzled scientists for decades, one that challenges everything we think we know about reality itself. Imagine this: over 68% of the energy in our universe is completely missing. It's not hiding behind a galaxy or buried in some distant nebula. It's simply gone. We can measure its gravitational effects, we can see its fingerprints on the fabric of space-time, but we have no idea what it actually is. This isn't just a small gap in our knowledge, it's a gaping hole in the very foundation of physics. We call this elusive force dark energy, and its discovery turned cosmology upside down. Think about it: everything you see around you, from the stars in the heavens to the device you're watching this on, accounts for less than 5% of the universe. The rest invisible, undetectable, and utterly mysterious. It's as if we've been reading a thrilling novel only to realize that 2/3 of the pages are blank. But here's where things get even more fascinating. Scientists haven't given up. In fact, the hunt for answers has sparked some of the most creative, daring, and downright bizarre theories in the history of science. Some sound like they're straight out of a science fiction epic, while others twist the laws of physics in ways that bend the mind. That's exactly what we're exploring today. We're going on a journey through 30 of the most compelling theories about the universe's missing energy, ideas that range from revolutionary to revolutionary strange. We'll dive into concepts like phantom energy, quantum fluctuations, extra dimensions, and even the possibility that our universe is just one bubble in an infinite cosmic foam. This isn't just a list of guesses, it's a tour of the cutting edge of human curiosity, where imagination and evidence collide. So whether you're a seasoned space enthusiast or someone who's just curious about the cosmos, you're in for a ride. By the end of this, you'll not only understand why dark energy is such a monumental puzzle, you'll see just how far we're willing to go to solve it. Our journey begins not in the vast emptiness of space, but in the mind of one of history's greatest physicists. Albert Einstein, while developing his theory of general relativity, encountered a problem. His equations suggested a universe that was either expanding or contracting, but the scientific consensus at the time, including his own belief, was that the universe was static and eternal. To make his math match this prevailing idea, he introduced a fudge factor, a repulsive force that would counterbalance the attractive pull of gravity on the largest scales. He called this the cosmological constant, and he later reportedly declared it his greatest blunder once Edwin Hubble discovered the universe was in fact expanding. For decades, the cosmological constant was seen as a historical footnote, a brilliant mistake. But then, in 1998, everything changed. Two independent teams studying distant supernova made a staggering discovery. The expansion of the universe isn't slowing down due to gravity as everyone thought. It's actually accelerating. Something was pushing galaxies apart from one another at an ever-increasing rate. Suddenly, Einstein's blunder didn't look so foolish after all. Physicists realized that his cosmological constant could perfectly describe this mysterious repulsive energy, a uniform energy density inherent to the vacuum of space itself. Think of it like this: imagine space isn't just an empty stage where the drama of the universe plays out. Instead, imagine the stage itself is alive with a faint, invisible energy. Even in a perfect vacuum, completely devoid of matter, this energy would still be there, woven into the very fabric of reality. This isn't a force that pushes in the traditional sense. It's a property of space that causes new space to form. And as more space appears, the repulsive effect grows stronger, leading to that accelerating expansion we observe. In modern terms, we try to explain this using quantum field theory, which suggests that what we perceive as empty space is actually a seething, bubbling foam of virtual particles. These are particle-antiparticle pairs that constantly pop into and out of existence, borrowing energy from the vacuum for an incredibly brief moment. The combined energy of all these fleeting quantum fluctuations could theoretically manifest as the cosmological constant. There's just one enormous problem. When physicists calculate how much energy this quantum foam should contain, the number they get is wrong. Not just a little wrong, it's off by a factor of 1 followed by 120 zeros. It is arguably the worst theoretical prediction in the entire history of science. This monumental discrepancy is a clear sign that while the cosmological constant is a compelling idea, our understanding of the quantum vacuum and how it gravitates is profoundly incomplete. But what if Einstein's constant isn't the final answer? What if the energy of the vacuum isn't, well, constant at all? This line of questioning brings us to a fascinating and elegant alternative known as quintessence. The name itself is a nod to antiquity. Ancient philosophers believed the heavens were made of a fifth element, a perfect substance distinct from the earth, air, fire, and water of our terrestrial world. Modern cosmologists have borrowed this poetic term for a theory that is just as profound. Unlike the static, unchanging cosmological constant, quintessence proposes that dark energy is a dynamic, evolving force field that permeates all of space. Imagine the difference between a still photograph and a feature film. The cosmological constant is like that single, frozen image, a fixed value that has remained the same since the dawn of time. Quintessence, on the other hand, is the entire movie. It's a scalar field, meaning it has a value that can vary across time and space, much like the Higgs field that gives particles their mass. This field isn't made of particles. It's more fundamental, an underlying property of the universe that can change in strength. In the early cosmos, this quintessence field might have been weak, allowing gravity to dominate and pull matter together to form galaxies. But as the universe expanded and evolved, the energy density of this field could have changed, gradually becoming the dominant force that now drives acceleration. This dynamic nature is the theory's greatest strength because it offers potential solutions to some of the cosmological constant's most nagging problems. The first is the coincidence problem. Why is the density of dark energy roughly equal to the density of matter now, in this specific epoch of the universe's history? If it were a true constant, this would be a bizarre and unexplained coincidence. But if dark energy is dynamic, it could naturally evolve to become dominant at around this time. The second advantage is flexibility. A changing field can be tuned to match a wider range of observational data. For instance, the equation of state for a cosmological constant is fixed, but quintessence allows for a value that can change over billions of years, which might align better with subtle details we observe in the large-scale structure of the universe. There are many models for how this quintessence field might behave. Some suggest it slowly rolls down a potential energy hill, like a ball gradually descending a gentle slope, its energy density decreasing at a precise rate. Others propose more complex interactions where the field couples to matter or even to itself. There are even tracker models where the quintessence field's energy density naturally follows or tracks the energy density of radiation and matter for most of the universe's history, only recently breaking away to initiate the accelerating expansion we see today. This ability to potentially explain the when and why of dark energy's dominance makes quintessence a powerful and compelling contender in the quest to solve this cosmic mystery. While quintessence offers a dynamic and evolving vision of dark energy, some theories push the concept to an even more dramatic extreme. Enter phantom energy, a hypothetical form of dark energy so potent and bizarre that its existence would guarantee a cataclysmic end for the entire cosmos. To understand phantom energy, we need to look at a specific value in cosmology known as the equation of state parameter, represented by the letter W. This number describes the relationship between the pressure and density of dark energy. For Einstein's cosmological constant, W is exactly -1. But phantom energy proposes a value that is less than -1, meaning its pressure is even more negative. This might sound like a minor tweak to an equation, but its implications are anything but small. This more negative pressure suggests a substance with what theorists call negative kinetic energy. In simpler terms, the more space expands due to phantom energy, the stronger and more powerful the phantom energy itself becomes. It's a terrifying positive feedback loop on a universal scale. Imagine you're trying to inflate a balloon, but the act of blowing air into it doesn't just stretch the rubber, it actually makes your lungs stronger. You blow harder, which makes your lungs even stronger, forcing you to blow harder still, in a cycle that quickly spirals out of control. That's essentially what phantom energy would do to the fabric of spacetime itself. This runaway acceleration leads directly to a hypothetical doomsday scenario for the universe known as the Big Rip. If phantom energy is real, then the expansion of the universe wouldn't just continue to accelerate, it would accelerate infinitely. About 60 million years before the end, the accelerating expansion would become so powerful that it would overcome the gravitational forces holding our local group of galaxies together, tearing them apart. Galaxies would be flung into the ever-expanding void, isolated from one another. Then, just months before the finale, the terrifying force would rip apart individual galaxies, pulling stars away from each other. In the final minutes, the expansion would tear stars and planets apart, and in the last inconceivable moments, atoms, nuclei, and ultimately the very fabric of spacetime would be ripped apart. The universe would end not with a collapse or a freeze, but with a catastrophic shredding of every single structure that ever existed. The theoretical basis for such an outrageous idea often comes from considering certain types of scalar fields, similar to quintessence but with a specific, peculiar potential energy. Some models in string theory also allow for such states, yet for all its dramatic appeal, phantom energy faces significant hurdles. Many physicists view it as theoretically unstable, as it could allow for violations of fundamental energy conditions and open the door to time travel and other paradoxes. Current observational data from telescopes like Planck and measurements of supernova consistently point to a value of W very close to -1 with a small margin of error. So far, the data doesn't strongly support the phantom energy hypothesis, but it also doesn't completely rule it out. The possibility, however remote, that the universe is destined for such a violent and absolute end ensures that phantom energy remains one of the most chilling and fascinating ideas in modern cosmology. But what if we've been approaching this entire puzzle from the wrong angle? Instead of searching for a mysterious new form of energy, perhaps the answer lies in rewriting one of the most fundamental rules of the universe itself, gravity. This is the radical proposition of modified Newtonian dynamics, or MOND. For centuries, we've relied on Newton's law of universal gravitation, which states that the gravitational force between two objects weakens with the square of the distance between them. This law works perfectly within our solar system, accurately predicting the orbits of planets. But when we look out at the vast, spinning disks of galaxies, something is very wrong. The stars at the outer edges of galaxies are moving so fast that, according to Newton's and Einstein's laws, the immense gravitational pull of all the visible matter in the galaxy shouldn't be nearly strong enough to hold them in orbit. They should be flung off into intergalactic space, yet they aren't. The conventional solution is to propose the existence of dark matter, an invisible substance that provides the extra gravitational glue. MOND offers a different, elegant, and controversial fix. Maybe our equations for gravity are simply incomplete, and they break down at the incredibly low accelerations found in the outskirts of galaxies. The core idea of MOND introduces a new fundamental constant of nature, a critical acceleration threshold below which gravity begins to behave differently. Imagine driving a car. On a regular road, your acceleration is governed by the pressure you put on the gas pedal. But MOND suggests that on a cosmic scale road, where acceleration becomes incredibly tiny, like 100 billionth of the gravity we feel on Earth, the rules of acceleration change. Below this threshold, the force of gravity stops fading with the square of the distance and instead starts fading only with the distance itself. This tiny tweak to the math has a huge effect. It dramatically increases the gravitational force in the regions where accelerations are low, exactly where galaxies seem to need extra pull to hold onto their rapidly spinning outer stars. The most stunning success of MOND is its breathtaking ability to predict the rotation curves of a huge variety of galaxies using only their visible, ordinary matter. For many galaxies, you can plug in the distribution of stars and gas, apply MOND-modified formula, and out comes a prediction for how fast the stars should be rotating at every distance from the center. Time and time again, these predictions match the observed velocities almost perfectly without needing to invoke any invisible dark matter. It's a powerful and compelling argument that has kept the theory alive for decades. Furthermore, MOND has successfully predicted subtle details in the way galaxies move and interact, details that the standard dark matter model sometimes struggles with. However, this radical rewrite of gravity faces its own monumental challenges. The most significant is that while MOND excels at explaining the physics of individual galaxies, it has tremendous difficulty accounting for the evidence for missing mass on larger scales. Observations of colliding galaxy clusters, like the famous Bullet cluster, show that the gravitational lensing effect, where the cluster's gravity bends light from objects behind it, is strongest in regions that are largely devoid of visible matter. This is interpreted as direct proof of a dark matter halo that has become separated from the regular matter during the collision. For MOND to explain this, it would require a significant and complex modification, which so far has been elusive. Additionally, MOND in its original form does not naturally account for the precise patterns we see in the cosmic microwave background, the afterglow of the Big Bang, which are beautifully explained by the standard model of cosmology that includes both dark matter and dark energy. This has led some researchers to explore relativistic extensions of MOND, theories that attempt to build a full Einstein-level description of gravity that reduces to MOND in the right limit. These theories are highly complex and remain a topic of intense debate, representing a fascinating middle ground in the quest to understand what's truly governing the cosmos. Now, the quest to understand dark energy often involves introducing entirely new and exotic substances, but what if the solution was even more elegant? What if a single, unified entity could explain not one, but two of the universe's greatest mysteries? This is the ambitious promise of the Chaplygin gas. Imagine a cosmic fluid that possesses a truly bizarre property. It exerts negative pressure. The harder you try to squeeze it, the more it pushes back against you. This isn't just a theoretical curiosity. This unique characteristic allows it to play a dual role across cosmic history. In the dense, early universe, this fluid would have behaved just like cold, dark matter, clumping together under gravity to help form the very first galaxies. But as the universe expanded and thinned out, this same substance would have undergone a dramatic phase change, its repulsive, energy-like properties coming to the fore to drive the accelerated expansion we see today. One fluid, two completely different personalities, solving both the dark matter and dark energy problems in one grand, unifying sweep. The mathematical heart of this idea is surprisingly simple and is described by a straightforward equation of state linking its pressure and density. The model is named after a Russian physicist, Sergei Chaplygin, who first studied this type of equation in the early 20th century in the context of aerodynamics. It's a beautiful example of how an abstract piece of mathematics can find a completely unexpected application nearly 100 years later, solving a problem its creator could never have imagined. The most popular version in cosmology is known as the generalized Chaplygin gas, which introduces a couple of extra parameters that give theorists more flexibility to match the model with real-world astronomical data. This tweak allows the fluid to transition more smoothly from its matter-like state to its energy-like state, painting a more nuanced picture of how such a substance would evolve alongside the galaxies and clusters it helped to create. Of course, a theory this compelling must face the ultimate judge: observation. How well does the Chaplygin gas model actually match what we see in the sky? The results are a fascinating mix of promise and challenge. On one hand, the model does a remarkably good job of fitting the data from the cosmic microwave background and the large-scale distribution of galaxies. It can be tuned to reproduce the universe's expansion history in a way that looks very similar to the standard model. However, when astronomers look closer, they run into a significant problem. If this fluid is also supposed to act as dark matter and clump together to form the invisible halos around galaxies, it faces a serious issue: its sound speed. The speed at which pressure waves move through it is far too high. This means that small-scale structures like dwarf galaxies would have been smoothed out and prevented from forming in the early universe. It's a major hurdle that has led to various proposed fixes, such as adding a small amount of conventional dark matter back into the mix or introducing interactions between the Chaplygin gas and ordinary matter. But these adjustments inevitably chip away at the elegant simplicity that made the idea so attractive in the first place. Now let's return to that very first idea we explored, Einstein's cosmological constant. But this time, we're going to look under the hood, into the quantum engine that might be powering it. According to our most successful theory of the very small quantum mechanics, what we call a vacuum is anything but empty. Empty space isn't a void, it's a seething, chaotic, and incredibly active place. At every single point, for unimaginably fleeting moments, pairs of virtual particles and antiparticles are constantly blinking into and out of existence. They borrow energy from the vacuum itself, exist for a split second, and then annihilate each other, paying back the energy loan. This isn't some fringe idea. It's a well-established prediction confirmed by measurable effects like the Casimir force, where two metal plates placed incredibly close together in a vacuum are gently pushed together by the pressure of these quantum fluctuations outside them. This frantic activity means the vacuum of space should be brimming with energy. In fact, we can attempt to calculate just how much energy this quantum foam should contain. This calculated value is what we call the vacuum energy density, and it's the leading candidate for what the cosmological constant actually is. It's an incredibly elegant idea. The same quantum jitters that govern the behavior of atoms also provide the fuel for the universe's expansion. The math seems to line up perfectly. There's just one catastrophic, universe-sized problem. When physicists actually sit down and do the calculation, the number they get is utterly, incomprehensibly wrong. The predicted value of this vacuum energy is about 120 orders of magnitude. That's a 1 followed by 120 zeros, larger than the value we actually observe from measuring the universe's acceleration. To put that discrepancy into perspective, it's the difference between the energy contained in a single gallon of gasoline and the energy contained in the entire observable universe. It is, without a doubt, the most embarrassing and worst prediction in the entire history of theoretical physics. This yawning chasm between theory and observation is known as the cosmological constant problem, and it represents a fundamental crisis in our understanding of how gravity and quantum mechanics interact. It suggests that either our theories about the quantum vacuum are deeply flawed, or that some mysterious, perfect cancellation mechanism is at work, negating almost all of this immense energy for reasons we cannot fathom. Solving this problem is one of the holy grails of modern physics, because until we do, we can't truly claim to understand the universe at its most fundamental level. But if the vacuum energy calculation is so spectacularly wrong, perhaps we need a completely new paradigm to understand what's happening, a shift in our conception of reality itself. This brings us to one of the most mind-bending ideas in all of theoretical physics, the holographic principle. To grasp this, we have to start not with the vast cosmos, but with the enigmatic physics of black holes. In the 1970s, physicist Jacob Bekenstein made a startling proposal. A black hole must have entropy. Entropy is a measure of disorder or information content, and Bekenstein realized that a black hole's entropy is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it's proportional to the surface area of its event horizon, the two-dimensional boundary from which nothing can escape. This was a profound clue that the information needed to describe everything that falls into a black hole might somehow be encoded on its surface, not stored within its volume. This discovery eventually led to the full-blown holographic principle, championed by physicists like Gerard T. Hooft and Leonard Susskind. They proposed a radical idea that our perception of a three-dimensional universe might be a kind of illusion. All the information that describes everything within a volume of space, every star, every planet, every one of us, could be entirely encoded on a two-dimensional surface that surrounds that volume. Think of it like a hologram on your credit card. The image appears to have three-dimensional depth, but all the information to create that image is actually stored on a flat, two-dimensional surface. In this view, the entire universe is a cosmic hologram, a magnificent projection from a distant two-dimensional boundary. So what does this have to do with dark energy? The connection lies in those information storage limits. The amount of information that can be stored on any surface is finite. It's limited by the area of that surface, not its volume. In our expanding universe, the cosmological horizon, the maximum distance from which light has had time to reach us, defines our ultimate information boundary. As the universe expands, this horizon grows, and with it, the amount of information that can be encoded there. Some theorists, like Professor Yu Wang and others, have proposed that dark energy is not a substance at all, but a fascinating consequence of this fundamental information limit. The energy density of the vacuum, which drives acceleration, could be tied to the number of degrees of freedom or the amount of information available on this cosmological horizon. In this framework, the acceleration isn't caused by a mysterious fluid. It's an emergent property stemming from the way information is distributed and limited at the very edges of our observable reality. This idea finds a natural home within string theory, where the mathematics of holography is concretely realized through the famous AD/S/CFT correspondence. This is a powerful duality that shows a gravitational theory in a volume of space is completely equivalent to a quantum field theory without gravity living on its boundary. While this specific correspondence describes a universe with negative curvature, unlike our own, it provides a robust mathematical playground that demonstrates the holographic principle in action. It shows that our intuitive sense of three-dimensional reality might be a convenient but ultimately incomplete picture. The holographic approach to dark energy offers a potential pathway to solving the cosmological constant problem, as it fundamentally redefines what vacuum energy even is, linking it directly to the informational fabric of the cosmos rather than to a problematic sum over quantum fluctuations. It suggests that the missing energy isn't missing at all. We've just been looking for it in the wrong dimension, searching for a three-dimensional answer to what might ultimately be a two-dimensional question. This journey into the holographic principle reveals a universe where information is fundamental. But what if we take that idea even further? What if gravity itself, the force that sculpts the cosmos, isn't a fundamental force at all? This is the extraordinary proposal of entropic gravity, a theory put forward by physicist Eric Verland. To understand it, let's start with a simpler, everyday concept, entropy. Entropy is often described as a measure of disorder. but a more precise definition is that it's a measure of the number of ways a system can be arranged. It's also deeply connected to information. The famous second law of thermodynamics states that the total entropy of a closed system always increases over time. Things tend toward disorder. But why does this happen? It's almost as if nature has a preference for states that are more probable, more random. Now, imagine a very small particle, like a single atom, suspended in a bath of water. You'd see it jiggle and dance erratically under the bombardment of countless water molecules. This is Brownian motion, and in the early 1900s, Albert Einstein showed that this random motion is driven by entropy. The particle moves not because it's being pushed by a specific force, but because the entire system is evolving toward a state of higher entropy. The force we might associate with its movement isn't fundamental, it's emergent. It arises statistically from the microscopic chaos. Verlaine's brilliant leap was to ask, could the force of gravity be exactly the same kind of thing? Could gravity be an entropic force? Verlaine's theory suggests that gravity is not a fundamental interaction woven into the fabric of spacetime, as Einstein described. Instead, it's a consequence of nature's tendency to maximize entropy. How does this work? It goes back to the holographic principle and information. The idea is that the information describing a volume of space is stored on its boundary. When a massive object, like a star, is placed near that boundary, it disrupts the information stored there. It creates a kind of entropy gradient. According to Verlaine, gravity is the universe's way of responding to this disruption and restoring a state of maximum entropy. It's a force that emerges from the natural drift toward disorder, much like the pressure in a gas emerges from the random motion of molecules, not from some fundamental pressure force. The implications of this are staggering. First, it offers a potential explanation for the laws of inertia and Newton's famous laws of motion. In this view, an object in motion stays in motion not because of an abstract law, but because changing its state would require a change in the entropy of the underlying information structure of space, which nature resists. Second, and most crucially for our mystery, entropic gravity provides a breathtakingly simple and natural explanation for dark energy and the accelerating expansion of the universe. If gravity is an emergent phenomenon tied to the information on a boundary, then what happens as the universe expands? That boundary, the cosmological horizon, gets larger. As it grows, the amount of information it can hold increases and the entropy associated with it rises. This ever-increasing entropy, according to the logic of entropic forces, generates a repulsive pressure. This negative pressure driving the universe toward a higher entropy state is dark energy. The acceleration isn't caused by a mysterious substance. It's the inevitable thermodynamic consequence of an expanding universe whose information content is growing. It's a compelling and deeply unifying vision that links the behavior of the largest scales of the cosmos directly to the fundamental laws of information and thermodynamics. But to truly stretch our minds, we must venture beyond the familiar 3 dimensions of space and 1 of time. What if our entire universe is just a single slice of a much larger, higher-dimensional reality? This is the captivating premise of Braneworld cosmology, a set of ideas born from the mathematics of string theory. In these models, our 4-dimensional spacetime is not the entirety of existence. Instead, it's a membrane, or brane for short, a 3-dimensional surface floating within a higher dimensional bulk that could have many more spatial dimensions. We are, in a very literal sense, living on an island universe, but one that's adrift in an unimaginably vast cosmic ocean. This changes everything about how we think about gravity. In our brain, the particles that make up you, me, and all the stars are like pins stuck in a pincushion. They are trapped, unable to leave the surface of our 3-dimensional world. But gravity, according to some Braneworld models, is different. It might not be a force confined to our brain. Instead, it could be a vibration of the higher dimensional bulk itself. This means the gravitational field generated by every star and galaxy could actually be spreading out or leaking into these extra dimensions. From our perspective, trapped on the brane, this leakage would make gravity appear weaker than it truly is in the full higher dimensional space. Think of it like a water pipe with a slow, steady leak. If you're only measuring the water pressure inside the pipe itself, it seems lower than expected because some of the water is escaping into the surrounding ground. In the same way, the gravitational attraction we measure between objects in our universe might seem weaker because a portion of that force is dissipating into the extra dimensions. This elegant idea provides a potential explanation for why gravity is so unfathomably weaker than the other fundamental forces. It's not inherently weak, its strength is just being diluted across a larger spatial volume. So where does dark energy fit into this mind-bending picture? The leakage of gravity offers one pathway, but there's another, even more dynamic possibility. Our brane could be moving. If our universe is a dynamic object floating in the bulk, it might not be sitting still. It could be vibrating, twisting, or even expanding within these higher dimensions. The energy associated with this motion or with the curvature of the brane itself could manifest within our universe as a constant, pervasive energy density, a perfect candidate for the cosmological constant. Furthermore, our brane might not be alone. There could be other branes out there in the bulk, other entire universes floating parallel to our own. The gravitational influence of a nearby brane could gently tug on ours, creating a repulsive force that pushes our spacetime apart. In this scenario, the accelerating expansion of our universe isn't driven by an internal energy, but by the external gravitational pull of another world separated from us by a hidden dimension. It's a concept that feels pulled from the pages of science fiction, yet it emerges naturally from the profound mathematics of some of our most advanced physical theories. This brings us to one of the most radical and controversial challenges to the very foundations of physics, the idea that the universe's constants might not be so constant after all. What if the speed of light, that ultimate cosmic speed limit denoted by the letter c, has actually been slowing down over the vast expanse of cosmic history? This is the core of the time-varying speed of light, or VSL, theory. It's a proposal that directly confronts the dark energy problem by suggesting we've misinterpreted the evidence because we're using the wrong ruler. The speed of light is the fundamental conversion factor between space and time, woven into the fabric of Einstein's theories. If c were different in the past, it would change our interpretation of everything we see in the distant universe. Proponents of this idea, like physicist John Moffat, who pioneered the modern version in the 1990s, argue that a faster speed of light in the early universe could elegantly solve several cosmological puzzles at once. The most famous is the horizon problem, which asks why the universe looks so uniform in every direction. In the standard Big Bang model, distant regions of the cosmos could never have been in contact with each other to equalize their temperature because light wouldn't have had enough time to travel between them. Inflation theory solves this by proposing a brief period of ultra-rapid expansion. But a VSL theory offers an alternative fix. If light traveled immensely faster in the universe's first moments, then those distant regions could have easily communicated, smoothing everything out without needing a separate inflationary epoch. This faster speed would also alter how we perceive the expansion history of the universe. The observed acceleration could be an illusion caused by a gradual change in this fundamental constant. If light was faster when it left distant supernova billions of years ago, it would have taken less time to reach us than our current constant c models predict. This would make those supernova appear fainter and farther away than they truly are, perfectly mimicking the signature of an accelerating expansion driven by dark energy. In this view, we don't need a mysterious energy. We just need to realize our cornerstone constant has been shifting under our feet. Of course, a theory this revolutionary faces immense scrutiny and formidable obstacles. The constancy of the speed of light is not just an assumption. It's a foundational pillar of modern physics, supported by a vast web of experimental evidence and theoretical consistency. The entire structure of special relativity, with its famous equation E equals mc squared, depends on c being an immutable constant. If c has varied, it would send ripples through every branch of physics, forcing a rewrite of textbooks and challenging our understanding of causality itself. Furthermore, a changing speed of light would leave other observable imprints that astronomers can hunt for. One key test involves another fundamental constant, the fine structure constant, which governs the strength of electromagnetic interactions and is directly proportional to the speed of light. Precise measurements of the absorption lines in light from incredibly distant quasars have been used to check if this constant has changed over time. The results are complex and sometimes contradictory, with some studies suggesting a very tiny variation, while others show no change at all. This creates a tight constraint for VSL theories. Any change in the speed of light must be carefully tuned to also match these precise measurements of other constants, a challenge that has kept the theory on the fringe of cosmology. While it remains a captivating and intellectually daring alternative, it highlights the lengths to which physicists are willing to go in questioning absolutely everything to solve the profound mystery of dark energy. This brings us to a concept that is less about the mechanics of the universe and more about our place within it. What if the value of dark energy isn't determined by a fundamental law of physics, but is instead a random roll of the cosmic dice? And what if our very existence as observers is the only reason we find its value so peculiar? This is the core of the Entropic principle, a line of reasoning that shifts the question from why is dark energy this value to why do we find ourselves in a universe where dark energy has this value? The principle starts with a startling observation. The measured value of the cosmological constant is incredibly fine-tuned for the existence of life. If it were even slightly larger by just 1 part in 120, the universe would have expanded so rapidly after the Big Bang that matter would never have had a chance to clump together. No stars, no planets, and certainly no astronomers would ever have formed. The cosmos would be a cold, dark, and utterly empty void. On the other hand, if dark energy were significantly smaller or negative, the universe might have collapsed back in on itself in a big crunch long before life could evolve. We find ourselves in a breathtakingly narrow window where the repulsive force is strong enough to prevent a catastrophic collapse, but weak enough to allow for the formation of the complex structures that make our existence possible. This incredible fine-tuning seems to demand an explanation. The anthropic approach provides one by proposing that our universe might not be unique. Instead, it could be one tiny bubble in a vast and infinite multiverse, a cosmic landscape where the fundamental constants, including the strength of dark energy, are randomly set to different values in each separate region. In most of these universes, the constants are inhospitable. Some expand into nothingness instantly, while others collapse immediately. But in a vanishingly small fraction of these universes, the numbers just happen to line up correctly for galaxies to form and life to emerge. We, of course, can only find ourselves in one of those rare, life-permitting universes. Our observation of a seemingly improbable value for dark energy is therefore not a mystery to be solved. It is a selection effect, a necessary condition for us to be here to observe anything at all. This idea moves the goalposts of the debate from physics to philosophy. For some scientists, the anthropic principle is a cop-out, a way of avoiding the search for a deeper, more satisfying physical mechanism. They argue it makes the value of dark energy essentially unexplainable by traditional science. For others, it is the most rational conclusion, a profound acknowledgement that our observations are inherently biased by the very fact that we are conscious observers. It forces us to consider that the laws of nature we hold so dear might not be fundamental and universal laws at all. but rather local bylaws specific to our particular cosmic neighborhood. Whether one finds it deeply insightful or deeply unsatisfying, the anthropic principle remains a powerful and provocative lens through which to view the greatest mysteries of the cosmos, reminding us that sometimes the answer might not be found in the stars alone, but in the simple fact that we are here to look at them. Yet another approach questions whether we even need to invoke a new form of energy, suggesting instead that the answer has been hiding in plain sight within the complex tapestry of the universe itself. This is the theory of backreaction from inhomogeneities, and it proposes that dark energy might not be a mysterious substance, but rather a grand illusion created by the uneven distribution of matter across the cosmos. Einstein's equations, which form the bedrock of general relativity, were originally solved for a perfectly smooth and uniform universe, a simplifying assumption that makes the math manageable. But our actual universe is anything but smooth. It's a lumpy, clumpy place filled with vast cosmic voids hundreds of millions of light years across and dense concentrations of matter like galaxy clusters and superclusters. This theory asks a simple but profound question. What if the gravitational influence of these immense structures somehow reacts back on the overall expansion of the universe, altering it in a way that looks exactly like an accelerating force? To understand how this might work, picture a vast, undulating ocean. If you were to measure the average height of the ocean's surface from a satellite, you'd get a certain value. But if you were out on a boat, you'd be constantly riding up and down on massive waves and swells. The backreaction theory suggests that our standard model of cosmology is like measuring that average ocean height without fully accounting for how the energy contained within those rolling waves might affect the entire ocean basin over time. In our cosmic ocean, the voids are the troughs and the galaxy clusters are the crests. The gravitational pull within a dense cluster is incredibly strong, holding itself together. But the emptier voids, with their weaker gravity, expand faster than the average, pulling the fabric of spacetime apart from within. As the universe ages and these structures grow ever larger, their collective gravitational effect on the overall expansion rate might become significant, potentially creating a cumulative impact that mimics the presence of a dark energy driving an acceleration. This idea is compelling because it uses only the known ingredients of general relativity and ordinary matter. It doesn't require any new, undiscovered physics. The challenge, however, is monumental. The mathematics involved in calculating this backreaction effect for a realistically lumpy universe is ferociously complex, far beyond the smoothed-out equations used in standard textbooks. Different research groups using various approximation techniques have arrived at starkly different conclusions. Some calculations suggest the effect is real but far too small to account for the observed acceleration, amounting to perhaps only a few % of the required push. Others have proposed more radical models where the backreaction could be substantial, perhaps even sufficient to explain the entirety of the dark energy phenomenon without any cosmological constant at all. The debate is heated and remains entirely within the realm of theoretical computation, as directly measuring this subtle average effect across the entire observable universe is currently beyond our observational capabilities. The ultimate test for this theory will come from increasingly precise maps of the universe's large-scale structure and its expansion history. If backreaction is a major player, it might leave a unique fingerprint on the relationship between how fast the universe is expanding and how quickly cosmic structures are forming. Future missions like the European Space Agency's Euclid telescope will provide exquisite data that could either corner this elusive effect or rule it out as the primary culprit. It represents a brilliant and conservative line of inquiry, a reminder that before we invent entirely new physics to explain a phenomenon, we must first be absolutely certain we have exhausted the possibilities of the physics we already have. Now let's venture into one of the most abstract and mathematically beautiful corners of theoretical physics, a concept that sounds like it's from an alternate reality, unparticle physics. This idea, first proposed by Howard Georgi in 2007, asks us to imagine a substance that doesn't behave like any matter we know. We're familiar with particles, electrons, quarks, photons, all of which have a definite mass and obey specific quantum rules. But what if there existed something that wasn't made of particles at all? This is the realm of the unparticle, a scale-invariant substance that could be hiding in plain sight, subtly influencing the cosmos. Scale invariance is the key property here. Think about a fractal like a snowflake or a coastline. No matter how much you zoom in or out, it looks roughly the same. It has no defining scale or characteristic size. Unparticles are theorized to behave in a similar way. They don't have a specific mass. Instead, they manifest as a continuous spectrum of behavior, somewhere between a massless particle like a photon and a massive object with a defined weight. This makes them incredibly slippery and hard to detect, as they wouldn't leave sharp, distinct signals in our particle detectors like a proton or electron would. This bizarre stuff is thought to originate in what physicists call a hidden sector. Our entire visible universe, with all its known particles and forces, might be just one sector of a much larger reality. This hidden sector could contain its own particles and forces that barely interact with ours, communicating only through the feeblest of connections, most notably gravity. Under certain conditions, the forces within this hidden sector could become incredibly strong at high energies, causing the particles within it to lose their individual identities and condense into this scale-invariant unparticle stuff. So, how could this ethereal concept possibly be the source of dark energy? The connection lies in its gravitational influence and its equation of state. Due to its scale-invariant nature, the unparticle sector would have a unique relationship between its energy density and pressure. Theoretical calculations show that this relationship could result in a sustained negative pressure, the exact kind of repulsive effect needed to drive the accelerating expansion of the universe. Because it interacts so weakly with normal matter, it would be invisible to all our conventional experiments, yet its gravitational fingerprint would be everywhere, seamlessly blending into the signature we attribute to dark energy. While unparticle physics remains highly speculative, it represents a breathtakingly creative attempt to tackle the problem. It doesn't just add a new particle to the existing menu, it proposes an entirely new form of existence governed by different rules. It's a powerful reminder that the solution to our greatest cosmic mysteries might not lie in simply tweaking the parameters of our current models, but in being brave enough to imagine a reality that is far stranger and more wonderful than we have ever conceived. While unparticles propose a radically new form of existence, another theory suggests the answer might lie in a cosmic chameleon, a force that changes its very nature depending on its surroundings. This is the elegant idea behind the symmetron, a hypothetical light scalar field that could seamlessly explain why dark energy's effects are so dominant in the vast cosmic voids, yet completely invisible within our own solar system. The symmetron's behavior is governed by a process known as screening, a mechanism that allows it to hide in plain sight. In regions of high matter density, like here on Earth or within a galaxy, the presence of so many atoms suppresses the symmetron field, forcing it into a state of symmetry where it exerts no force on its surroundings. It effectively cloaks itself, making it undetectable by local experiments. But in the immense, near-perfect vacuum of the cosmic voids that stretch between galaxies, where the average density is less than a single atom per cubic meter, the field is unleashed. Here, far from the influence of matter, the symmetry is broken, and the field can take on a non-zero value, filling the void with a constant energy that drives the expansion of space itself. The beauty of this mechanism is that it naturally solves one of the biggest puzzles of dark energy. Why don't we feel its effects locally? If dark energy is a uniform energy permeating all of space, its repulsive force should be acting on everything, including the planets in their orbits or even the atoms within our own bodies. Yet we see no evidence of that. The symmetron elegantly explains this by being environmentally aware. It's not active where we are. It only switches on its dark energy behavior in the emptiest places in the universe, which coincidentally make up the vast majority of its volume. This makes it a compelling example of a broader class of theories known as modified gravity or fifth force models, which often employ similar screening mechanisms like the closely related chameleon field. What makes the symmetron particularly exciting for physicists is that it's not just a clever idea, it's a testable one. Because it is a field that can mediate a force, it could potentially produce a detectable fifth force in addition to the four fundamental forces of nature. The challenge is that its effects are screened in high-density environments, so we have to be incredibly clever to find it. The key is to design experiments that can peer into the field's hiding places. One method is to use extremely precise torsion balance experiments, which measure the tiny twist of a fiber suspended in a vacuum chamber to detect minuscule forces between objects. By conducting these experiments in a chamber emptied of as much air as possible, we create a local low-density environment that might allow the symmetron field to manifest, revealing itself as an unexpected attraction or repulsion between test masses. Another frontier for testing this idea is in space. Satellite-based experiments free from the constant gravitational and seismic noise of Earth can achieve sensitivities impossible in any terrestrial lab. By carefully measuring the orbits of planets and moons with exquisite precision, astronomers can hunt for any deviations from the predictions of general relativity that might be caused by the subtle influence of a screened scalar field like the symmetron. Furthermore, the effects of such a field on the large-scale structure of the universe could leave a distinct imprint on how galaxies cluster together, a signature that powerful new telescopes like the Euclid Space Observatory will be searching for. This means the symmetron isn't just a theoretical curiosity. It's a hypothesis on the verge of being proven or disproven by a new generation of experiments, making it one of the most dynamic and promising avenues in the ongoing quest to solve the mystery of dark energy. But our exploration of dynamic fields doesn't end with quintessence. There exists an even more exotic and flexible generalization known as K-essence, a theory that twists the very definition of kinetic energy to produce the repulsive force we observe. The K stands for kinetic, and that's the key to this entire idea. In most physical theories, from a rolling ball to a speeding rocket, kinetic energy is straightforward. It's the energy of motion, proportional to the square of the object's velocity. But K-essence boldly proposes that for this mysterious cosmic field, the rules are different. It possesses what physicists call a non-canonical kinetic energy term, which is a sophisticated way of saying the relationship between its energy and its motion is bizarre and non-linear. This allows the field to exhibit behaviors that are simply impossible for any ordinary form of matter or energy. Imagine the difference between pushing a child on a swing and trying to push a car through thick mud. With a swing, the relationship between your push and its motion is direct and predictable. But with a car in mud, the resistance you feel isn't linear. A tiny push does almost nothing, but a powerful shove might suddenly get it moving. K-essence is like that cosmic car in the mud. Its kinetic energy isn't tied to the square of its rate of change. It can be a far more complex, arbitrary function. This peculiar property allows the field to act like a form of dark matter with negligible pressure in the dense early universe, helping to form structures, and then later to transition seamlessly into a state with strong negative pressure, dominating the cosmos and driving the accelerated expansion. It's a single actor that can play two completely different roles on the cosmic stage simply by changing how it moves through space and time. The dynamics of a K-essence field are governed by what's known as an axion, a mathematical function that encapsulates all its possible behaviors. Theorists can craft this function to solve specific cosmological problems. For instance, one popular model is known as the Dirac-Bornfeld or DBI action, which originates from string theory. This model naturally limits the field's velocity, preventing it from reaching unphysical values and behaving like the phantom energy we discussed earlier, which could avoid that cataclysmic Big Rip scenario. The flexibility of this approach is its greatest strength. By designing different functions for the kinetic term, physicists can create K-essence models that track the radiation density after the Big Bang, then shift to track the matter density during the era of galaxy formation, and finally switch on their dark energy behavior at precisely the right moment to explain our observations today. This makes it a powerful tool for addressing the coincidence problem. Of course, a theory this flexible must be constrained by real-world data, and the most stringent test comes from the cosmic microwave background. The precise patterns in this ancient light are a fossil record of the universe's early conditions, and any viable dark energy model must be able to reproduce them. The good news for K-essence is that because it can be tuned to behave just like a cosmological constant at late times, it generally fits the observed CMB power spectrum very well. However, its presence can also subtly influence the integrated Sachs-Wolf effect, a specific feature of the CMB caused by photons gaining or losing energy as they travel through evolving gravitational potentials. Future, more precise measurements from next-generation observatories will be crucial for testing the specific predictions of various K-essence models and determining if this exotic kinetic energy is more than just a mathematical curiosity and is indeed the engine driving our accelerating universe. Now, what if we consider a form of energy so strange that its very existence requires particles that move faster than light? This brings us to the mind-bending concept of tachyonic fields. The name comes from the hypothetical tachyon, a particle that, unlike anything in our standard model, always travels faster than light. In the world of relativity, such an object would have a very bizarre property. Its mass squared would be a negative number. This isn't just a mathematical quirk, it implies a profound instability in the vacuum of space itself, and it's from this instability that some theories suggest dark energy could emerge. Imagine a perfectly smooth hilltop. A ball sitting on top of that hill is in a state of unstable equilibrium. The slightest nudge will send it rolling down into the valley below, seeking a stable, lower energy state. In quantum field theory, the Higgs field is like a ball that has already rolled down into a stable valley, giving particles their mass. A tachyonic field, however, is like a ball perpetually perched on that unstable hilltop. The field's potential energy is shaped in such a way that its lowest energy state isn't at zero, but at some other value, and the universe is constantly trying to roll towards it. This rolling, this dynamic evolution of the field, could be the source of the repulsive pressure we call dark energy. It's a concept deeply rooted in string theory, where such unstable fields, known as tachyons, often appear in the spectra of non-standard configurations of strings and branes, signaling an instability that the system must resolve. Of course, the biggest hurdle for any tachyon-based theory is the issue of stability. A field with a negative mass squared is inherently unstable, prone to runaway excitations that could have catastrophic consequences. To make a viable cosmological model, physicists have to carefully engineer the field's potential energy landscape. The goal is to create what's known as a tachyonic condensate, a state where the field settles into a stable configuration at the bottom of its potential well, and its energy density behaves like a cosmological constant. This is a delicate balancing act, ensuring the field doesn't decay too quickly or produce exotic particles that would have been detected. In some models, this tachyon field could even be related to the open strings that live on a D-brane in string theory, providing a concrete, though highly advanced mathematical foundation for this exotic idea. When it comes to making real-world predictions, tachyonic dark energy models have a distinct signature. Unlike a simple cosmological constant, a dynamical tachyonic field would have an equation of state parameter W that evolves over time. In many models, it starts at a value very close to zero, behaving almost like cold dark matter, which could have helped with the initial clustering of matter. Then, as the universe expands, it transitions to a state with a strong negative pressure driving the acceleration. This evolution could leave a detectable imprint on the large-scale structure of the universe, subtly affecting how galaxies cluster together over immense distances. Future observatories like the Vera C, Rubin Observatory and the Euclid Space Telescope will map the cosmos in unprecedented detail, and one of their key missions is to precisely measure any deviation of W from -1. If they find compelling evidence that dark energy's strength has changed over billions of years, it could be a major point in favor of a dynamic field like the tachyon, offering a breathtaking connection between the accelerated expansion of our universe and the deepest, most theoretical realms of quantum gravity. One of the most profound shifts in thinking about gravity doesn't just modify the equations we already have, it completely reimagines gravity's very nature, suggesting it isn't a fundamental force at all. This is the radical core of emergent gravity, a perspective that views the force that holds planets in orbit and bends starlight not as a primary ingredient of the universe, but as a secondary effect, a phenomenon that emerges from something even more basic, much like the concept of temperature emerges from the random motion of molecules. In this view, gravity and even space-time itself are not the foundation of reality. They are a kind of collective illusion, a holographic projection from a hidden, deeper layer of quantum information. To grasp this, think about what happens when a massive object sits in space. According to Eric Verland's formulation of entropic gravity, the object doesn't exert a pull because of a fundamental force. Instead, its presence disrupts the entropy or the information content associated with that region of space. In the holographic picture, all the information describing the volume of space containing the object is encoded on its boundary. The object's mass changes the amount of information on that boundary, creating an entropy gradient. Gravity, then, is not a force that pulls, but an entropic force, a spontaneous response by the system to return to a state of maximum entropy. Much like the elastic force in a stretched rubber band is a response to return to its relaxed state. The apparent attraction we call gravity is simply the universe's tendency to maximize its disorder. The connection to dark energy within this framework is both elegant and natural. If gravity is an emergent force tied to the information on a boundary, then the accelerating expansion of the universe finds a straightforward explanation. As the universe expands, the cosmological horizon, the ultimate information boundary for our observable universe, grows larger. This increasing boundary area allows for more information to be stored, which means the total entropy of the universe is increasing. This ever-rising entropy, according to the principles of emergent gravity, naturally generates a repulsive pressure. This negative pressure isn't caused by a mysterious substance called dark energy. It is the inevitable thermodynamic consequence of an expanding universe whose information content is growing. The acceleration is a side effect of the cosmos's relentless drive toward higher entropy. This idea finds a powerful echo in the recent research of physicists like Claudia de Ram and her work on massive gravity. While not identical to entropic gravity, massive gravity is another theory where gravity's behavior emerges from a specific structure, in this case from a graviton with a tiny mass. The fascinating link is that certain formulations of massive gravity can naturally produce a self-accelerating expansion of the universe without the need for a cosmological constant. The graviton's mass itself provides a constant energy density that permeates the vacuum of space, offering a compelling alternative origin story for the observed acceleration that is deeply connected to the particle nature of gravity itself, further supporting the notion that gravity's effects can emerge from its underlying properties. Emergent gravity represents more than just a new theory. It's a fundamental paradigm shift that connects the behavior of the largest scales of the cosmos directly to the laws of information and thermodynamics. It suggests that the solution to the dark energy puzzle might not require discovering a new particle or field, but rather a deeper understanding of how the most familiar force in the universe actually comes to be. It posits that the cosmos is ultimately built not on a fabric of space and time, but on a substrate of quantum information, and from that substrate, everything we see and feel, including the mysterious push of dark energy, naturally arises. What if dark matter and dark energy aren't two separate, unrelated mysteries, but two different faces of the very same single substance? This is the brilliant and ambitious proposal of dark fluid theory, a concept that seeks to unify the cosmos's two greatest puzzles into one elegant framework. Imagine an exotic, cosmic fluid that flows through the universe, invisible to our telescopes, yet dictating the fate of everything we see. In the dense, crowded neighborhoods of galaxy clusters, this fluid behaves exactly like cold, dark matter, clumping together under its own gravity to provide the extra pull that holds fast-spinning galaxies together. But out in the immense, empty voids between these clusters, where matter is spread incredibly thin, this same fluid undergoes a dramatic transformation. Its pressure turns negative and it begins to act as a repulsive force, pushing space itself apart and driving the accelerated expansion we attribute to dark energy. One fluid, two completely different personalities, each revealing itself depending on the environment, a cosmic chameleon that is both the glue and the engine of the universe. The key to this bizarre behavior lies in its equation of state, the mathematical relationship between the fluid's pressure and its density. For most substances we know, this relationship is fixed. But a dark fluid would have an unusual dynamic equation of state that allows it to shift its properties. In regions of high density, its pressure is negligible, so it collapses under gravity just like particulate matter. In low-density regions, its pressure becomes strongly negative, causing it to resist gravity and generate a repulsive effect. This environmental switching mechanism is the theory's greatest strength, offering a potential solution to the cosmic coincidence problem. Why are the densities of dark matter and dark energy so similar in our current epoch? In this model, it's no coincidence at all. They are literally two aspects of the same underlying substance, naturally evolving together over time. The most famous and well-studied candidate for this unifying dark fluid is the generalized Chaplygin gas, a model named after a Russian physicist but resurrected for cosmology decades later. Its equation of state produces exactly this dual behavior, and it can be finely tuned with parameters to match astronomical observations. While it faces challenges, particularly in explaining the formation of small-scale structures like dwarf galaxies, its elegant simplicity keeps it a compelling target for research. Beyond this specific model, the dark fluid concept opens the door to a universe that might be far simpler at its most fundamental level, suggesting that what we perceive as two separate, dominant unknowns could ultimately be traced back to a single, unified component of reality, waiting for us to decipher its unique and complex language. Now, what if the key to unlocking the mystery of dark energy isn't about adding something new to the universe, but about changing our fundamental understanding of how gravity itself operates on the very largest scales? This is the compelling proposition of F of R gravity, a class of theories that takes Einstein's magnificent equations and asks a simple but profound question. What if the most famous ingredient in his recipe isn't quite right? In Einstein's general relativity, the curvature of spacetime is directly proportional to the matter and energy within it, and this relationship is governed by the Einstein-Hilbert action, which contains a specific term, the Ricci scalar, denoted by the letter R. This scalar is a single number that represents the overall curvature at any point in spacetime. F of R gravity proposes a bold modification. It replaces this simple r with an arbitrary function of r written as f of r. This tiny change in the mathematical foundation has monumental consequences for how gravity behaves across cosmic distances. Imagine you've been using a simple, reliable recipe for chocolate chip cookies your entire life. One day, you decide to experiment by replacing the standard sugar with a more complex sweetener like honey or maple syrup. The result is still a cookie, but its texture, spread, and taste are fundamentally different. F of r gravity does the equivalent with the universe's recipe. By changing the functional form of r, it alters how space-time responds to energy and matter, especially in environments where the curvature is very weak, like the vast, near-empty expanses between galaxies. In these low-density regions, the modified equations can generate an extra repulsive term, a kind of built-in cosmic pressure that drives the accelerated expansion of the universe. In this view, there is no dark energy fluid. There is only gravity, but gravity that behaves differently than Einstein envisioned when the curvature is small. This approach is incredibly powerful because it uses only the known ingredients of general relativity and ordinary matter. It doesn't require inventing a new, undetected substance. It simply suggests that our theory of gravity is incomplete and needs a tweak that only becomes apparent on cosmological scales. The challenge, however, is that any such modification must still pass stringent tests closer to home. Our solar system is a laboratory where Einstein's original equations have been exquisitely verified for over a century. The precise orbit of Mercury, the bending of starlight around the Sun, and the data from lunar laser ranging experiments all agree with the predictions of standard general relativity. A successful F of r theory must therefore include a clever mechanism, often called a chameleon effect, where the modified behavior is suppressed in regions of high curvature and density, like our solar system, and only switches on in the low-density environments of intergalactic space. This ensures the theory remains ghost-free and avoids theoretical instabilities while perfectly matching both local precision tests and large-scale cosmological observations. The development of these theories is a tightrope walk between innovation and consistency. Cosmological data, particularly the precise measurements of the cosmic microwave background from missions like Planck, place very tight constraints on what these functions can look like. The theory must accurately reproduce the observed expansion history of the universe and the intricate patterns of galaxy clustering. Some of the most popular models, like the Hu-Sawicki model, are carefully designed to mimic a cosmological constant at late times, ensuring they match the observed acceleration, while also including a chameleon screening mechanism to satisfy solar system tests. The ongoing quest is to find a specific, viable function that seamlessly reconciles all these constraints, a task that continues to drive theoretical research and inspire new, more precise astronomical missions designed to probe the very nature of gravity itself. This concept of modifying gravity leads us to a truly foundational question. What if the very rules of the game aren't fixed? We've been operating under the assumption that the fundamental constants of nature, those unchanging numbers that dictate the strength of forces, are indeed constant. But what if that's the greatest assumption of all? This brings us to a radical class of theories that propose the gravitational constant itself, big G, may not be so constant after all. The idea is that the strength of gravity could be slowly weakening over the immense span of cosmic history. If gravity was stronger in the past, it would have pulled matter together more effectively in the early universe, influencing how structures formed. But as gravity weakens, its grip on the cosmos loosens. This gradual diminishment of the universal attractive force could, in effect, mimic the presence of a repulsive dark energy, as the weakening pull of gravity would make it seem as if something else is pushing the universe apart. The theoretical motivation for such a varying constant often comes from the very attempts to unify gravity with the other fundamental forces. In many attempts at a grand unified theory or within the framework of string theory, the constants we observe in our four-dimensional world are not truly fundamental. They are the result of how extra dimensions are compactified, or they are related to the vacuum expectation value of a field, like the Higgs field gives particles mass. If that underlying field can evolve over time, then the constant it determines, like the strength of gravity, could evolve with it. In this view, the gravitational constant isn't a fixed number but a dynamical quantity, a cosmic dial that has been slowly turning since the Big Bang. Of course, a claim this extraordinary requires extraordinary evidence, and scientists have devised incredibly precise methods to test it. One of the most powerful tests comes from our own solar system. The motion of the planets, especially the precise orbit of the Moon as measured by laser-ranging experiments that bounce light off reflectors left by the Apollo missions, provides a very tight constraint on how much G could have changed. These measurements tell us that any change in the gravitational constant must be incredibly slow, less than 1 part in 100 billion per year. Another crucial piece of evidence comes from the study of ancient stellar fossils, white dwarf stars. The luminosity of a white dwarf is directly tied to the strength of gravity during its formation. By comparing the brightness of very old white dwarfs with newer ones, astronomers can look for any discrepancy that would point to a different value of G in the past. So far, these observations have all reinforced the idea that G is indeed remarkably constant, placing severe limits on how much it could have varied and thus challenging the simpler versions of these theories. However, the story doesn't end there. Some sophisticated models propose a more nuanced variation, where the change in G is coupled to the expansion of the universe itself. In these theories, the variation might be more significant in the very early universe or in the extremely low-density environments of the cosmic void, potentially evading the tight constraints from our local, matter-rich solar system. Furthermore, a varying G would leave a distinct imprint on the cosmic microwave background. The precise patterns of hot and cold spots in this ancient light are a sensitive probe of the universe's physics during the first 400,000 years. A changing gravitational constant would alter the way gravity competed with radiation pressure to form those first ripples, changing the resulting power spectrum in a way that missions like Planck have been designed to detect. While the standard model of a constant G fits the data beautifully, the hunt for any tiny residual deviation continues, driving ever more precise observations to see if the universe's most familiar force might still have a secret, slowly fading history. Now, let's shrink our focus from the cosmic scale down to the quantum realm, to a phenomenon so strange it makes the vacuum of space an active participant in the universe's story. This is the Casimir effect, a quantum curiosity that might just hold a key to understanding the energy of nothingness itself. Picture two uncharged, perfectly smooth metal plates placed incredibly close together in a perfect vacuum, separated by a gap smaller than the width of a human hair. According to classical physics, nothing should happen between them, but the quantum world is never that simple. We know that the vacuum is not truly empty. It's a seething foam of virtual particles constantly blinking in and out of existence. These are not particles in the usual sense, but fleeting fluctuations in quantum fields that borrow energy from nothing for an infinitesimally short time. The magic of the Casimir effect arises because these two plates impose a boundary on this quantum frenzy. Outside the plates, any wavelength of virtual particle can appear. But in the narrow gap between them, only certain wavelengths can fit, much like how only certain musical notes can resonate in a pipe of a specific length. This means there are more possible virtual particle fluctuations outside the plates than between them, with more activity pushing inward from the outside than there is pushing outward from the inside. The net result is a tiny but measurable force that pushes the two plates together. It's a genuine physical force generated entirely by the restless energy of the quantum vacuum. The breathtaking leap in cosmology is to ask, could a similar effect, but on a universe-sized scale, be responsible for dark energy? Instead of two metal plates, imagine the boundaries of the observable universe itself. Some theorists propose that the cosmological horizon, the farthest distance from which light has had time to reach us, could act as a kind of cosmic Casimir plate. The quantum fluctuations inside this bounded volume of space would be restricted compared to what might exist beyond it, potentially creating a pressure differential. This difference in vacuum energy density between the interior of our observable universe and whatever lies beyond could manifest as a constant, repulsive force acting on the fabric of spacetime itself, driving the accelerated expansion we measure. This line of thinking provides a potential, albeit highly speculative, link between the bizarre but proven physics of the Casimir effect and the grand mystery of dark energy. It frames the cosmological constant not as an arbitrary number inserted into Einstein's equations, but as a potential consequence of the universe's own finite size and the quantum rules that govern its boundaries. However, the challenges are immense. The Casimir force we measure in the lab is attractive and incredibly weak, acting over microscopic distances, while dark energy is repulsive and operates across billions of light years. Bridging this gap requires a sophisticated theoretical framework that can scale this quantum effect to a cosmological magnitude, a task that remains at the very frontier of theoretical physics. Yet it stands as a powerful testament to how insights from the very smallest scales might eventually illuminate the very largest mysteries of the cosmos. Now, let's explore an idea that has captivated particle physicists for decades. A theory so elegant it promised to solve multiple problems at once, including perhaps the greatest of them all. This is supersymmetry, often called SUSY for short. At its heart, supersymmetry is a beautiful and profound proposal about the fundamental symmetry of the universe. It suggests that for every known particle in the standard model, like electrons, quarks, and photons, there exists a hidden superpartner particle. For an electron, there would be a selectron, for a quark, a squark, for a photon, a photino. These superpartners would be identical in every way to their standard counterparts except for one crucial property, their spin, a fundamental quantum characteristic. This pairing would create a perfect balance between the two great classes of particles, the fermions that make up matter and the bosons that carry forces. The implications of this symmetry are breathtaking. For one, it provides a perfect candidate for the universe's missing dark matter. The lightest of these superpartner particles, often called the neutralino, would be stable, neutral, and only interact through gravity and the weak force, making it virtually invisible and a perfect fit for the cold dark matter that seems to hold galaxies together. But its potential role doesn't stop there. Supersymmetry also offered what many physicists believed was the most promising solution to the catastrophic cosmological constant problem we discussed earlier. Remember the calculation that vacuum energy should be 120 orders of magnitude too large. Supersymmetry, if it were an unbroken symmetry of nature, would elegantly cancel this problem out. In a perfectly supersymmetric world, the contributions to the vacuum energy from particles and their superpartners would be exact opposites. They would perfectly negate each other, resulting in a net vacuum energy of precisely zero. It's a stunningly beautiful mathematical cancellation, a cosmic symmetry so powerful it could erase the most embarrassing discrepancy in all of physics. But here's the catch, and it's a monumental one. We do not live in a perfectly supersymmetric world. If we did, we would have already detected these superpartner particles because they would have the same mass as the electrons and quarks we know. Thus, electron would be as easy to find as the electron. Clearly, this is not the case. This means that supersymmetry, if it exists at all, must be a broken symmetry. The superpartners must be much heavier than their standard model twins, which is why our most powerful particle colliders, like the Large Hadron Collider, have so far failed to produce them. And this act of breaking the symmetry, while necessary to match reality, shatters the very solution it promised. The exquisite cancellation of the vacuum energy no longer works perfectly. The contributions from particles and their now much heavier superpartners no longer cancel each other out exactly. Instead of yielding zero, the calculation now gives a value that is still enormous, just shifted by the scale of the supersymmetry breaking. We are left right back where we started, with a predicted vacuum energy that is astronomically larger than what we observe. This presents a profound puzzle. If supersymmetry is to be a true theory of nature, it must not only explain why we haven't seen these particles yet, but it must also incorporate a new mechanism to explain why the cosmological constant is so infinitesimally small after the symmetry is broken. Some theorists suggest that within the vast landscape of possible ways to break supersymmetry, there might be special configurations where the cancellation is nearly perfect, leaving behind just the tiny trickle of energy we see as dark energy. Others see supersymmetry not as the final answer, but as a crucial stepping stone to an even deeper theory, like string theory, where the true resolution of the cosmological constant problem might be found. The ongoing search for any sign of supersymmetry at particle colliders is therefore about much more than just completing the standard model. It's a search for a key that might unlock our understanding of the vacuum itself and the mysterious energy that seems to be woven into its fabric. Now let's journey into the realm of the incredibly small and subtle to meet a hypothetical particle that could be influencing the very largest scales of the cosmos. We're talking about actions, or more generally, axion-like particles. These aren't your typical particles. They are theorized to be incredibly light, almost ghostly entities that barely interact with normal matter. Their original claim to fame was solving a deep and perplexing mystery in quantum physics known as the strong CP problem, which essentially asks why the strong nuclear force that holds atomic nuclei together seems to treat particles and their mirror image antiparticles exactly the same. The proposed solution was a new, very light particle that would essentially clean up this tiny asymmetry, making the equations work perfectly. While the original action conceived for this problem hasn't been found, the broader concept of these light, wispy particles has taken on a life of its own in cosmology. So how could something postulated to fix a problem in nuclear physics possibly be connected to the accelerating expansion of the universe? The connection lies in their potential to act as a dynamic dark energy field, much like the quintessence we discussed earlier. An axion-like particle isn't just a point-like object. It can be described by a field that stretches throughout all of space. Because these particles are predicted to be extraordinarily light, their associated field can be incredibly slow-rolling and feeble, yet pervasive. This makes it a perfect candidate for a quintessence field, one that could have been hiding in the background for billions of years, its energy density only becoming dominant recently to drive the cosmic acceleration. Its ultra-weak interactions with other matter would explain why we don't see any local effects from this energy, neatly solving one of the biggest puzzles. The potential doesn't stop there. Some of the most fascinating models involve what physicists call coupled dark energy. In these scenarios, the axion-like field doesn't just exist in isolation, it talks to dark matter. Imagine a cosmic dialogue where the dark energy field and the dark matter particles influence each other. This interaction could allow energy to be transferred between them, which would leave a distinct imprint on how structures form in the universe. For instance, this coupling could suppress the growth of galaxy clusters in a specific way or create a subtle, synchronized oscillation in the densities of both dark matter and dark energy over cosmic time. This offers a potential pathway to explaining the cosmic coincidence, why dark energy became dominant around the same time that sophisticated life emerged by linking the fate of dark energy directly to the behavior of dark matter. The search for these elusive particles is an active and thrilling frontier, While they are difficult to detect because they interact so weakly, scientists are employing incredibly ingenious methods. Some experiments are using powerful magnets to try and convert actions into detectable photons in a vacuum. Others are looking for the faint whispers of these particles in the precise properties of light from distant astrophysical objects. If an axion-like particle is indeed the source of dark energy, it would represent a breathtaking unification of physics, connecting the enigmatic rules that govern the atomic nucleus with the ultimate fate of the entire universe. It's a reminder that the solutions to our biggest cosmic mysteries might be hiding in the most delicate and subtle aspects of reality. But what if the two great shadows of the cosmos are not separate, silent actors, but are in constant, whispered conversation with one another? This brings us to a deeply fascinating possibility known as interacting dark energy. For decades, cosmologists have largely treated dark matter and dark energy as independent entities, each playing its own isolated role in the cosmic drama. One clumping together to form the gravitational scaffolding for galaxies, the other acting as a smooth, repulsive force pushing everything apart. But this approach leaves us with that nagging coincidence. Why are their energy densities roughly comparable in our present epoch? Interacting dark energy proposes a radical solution. Perhaps they are not independent at all. Perhaps these two unknown components are coupled, exchanging energy and momentum in a way that intimately links their fates and elegantly explains why we observe the universe we do today. The mechanics of this interaction are theorized to work through a direct coupling between the fields that represent dark energy and dark matter. Imagine a vast, invisible seesaw spanning the entire universe. On one end sits dark matter and on the other dark energy. In the early universe, when matter was densely packed, the seesaw was tilted heavily towards the dark matter side. But as the universe expanded and matter diluted, the interaction between them slowly began to transfer energy from the dark matter sector over to the dark energy sector. This continuous transfer would naturally cause the density of dark energy to become more significant at later times, elegantly addressing the timing of when it began to dominate the cosmic expansion. It's a dynamic process that replaces a bizarre coincidence with a logical, physical mechanism. This cosmic dialogue would leave profound and potentially detectable imprints on the universe. One major consequence would be a suppression in the growth of the largest cosmic structures. Dark matter's gravitational pull is what draws ordinary matter together to form galaxies and clusters. If interacting dark energy is steadily draining energy from the dark matter, it weakens dark matter's ability to clump together effectively. This would result in fewer massive galaxy clusters forming than we would expect in a standard non-interacting model. While current observations of cluster counts already place tight constraints on how strong this coupling can be, they don't rule it out entirely. A subtle suppression could still be hiding in the data, waiting to be teased out by the next generation of sky surveys. Furthermore, this interaction could introduce a new, synchronized oscillation in the densities of both dark components. As energy flows back and forth, it could create a faint, resonant signal, a kind of cosmic hum, embedded in the way galaxies are distributed across the universe. The hunt for this signal is like trying to hear a specific melody in a grand symphony. It requires incredibly precise maps of the universe's large-scale structure. Upcoming missions like the Euclid Space Telescope and the Vera-C Rubin Observatory are specifically designed to create these ultra-detailed maps, and one of their key goals is to search for the unique fingerprint of this dark sector interaction, a discovery that would forever change our understanding of the cosmos's hidden architecture. Beyond solving the coincidence problem, interacting dark energy models also offer a potential pathway to avoiding some of the more troubling futures for the universe, like the Big Rip. In some coupled scenarios, the transfer of energy can lead to a future where the expansion eventually slows down or enters a stable phase, rather than accelerating into a catastrophic singularity. The exploration of these models is a testament to the creativity of modern cosmology, demonstrating that the answers to our biggest questions may not lie in discovering two separate, monolithic entities, but in deciphering the complex and hidden relationship between them. Long before dark energy was even a concept, physicists were grappling with another cosmic mystery, the medium through which light was thought to travel. They called it the luminiferous ether, an invisible, frictionless substance that was believed to permeate all of space, providing a stationary frame of reference for the propagation of light waves, much like air carries sound. This idea was completely upended in the early 20th century by the famous Michelson-Morley experiment, which failed to detect any sign of this ether wind as Earth moved through space. Albert Einstein's theory of special relativity delivered the final blow, showing that the speed of light is constant for all observers and that there is no privileged frame of reference, seemingly banishing the ether to the history books as a scientific dead end. Yet, like a cosmic phoenix, the concept of an ether is being reborn in a startlingly modern form to address the puzzle of dark energy. Today's theorists aren't reviving the rigid, mechanical ether of the 19th century. Instead, they are exploring the possibility of a new kind of background field that pervades the universe, a subtle, dynamic medium that does not provide a universal rest frame, but still violates Lorentz invariance, a cornerstone of Einstein's relativity that states the laws of physics are the same for all observers moving at constant velocity. The idea is that this modern ether could pick out a preferred direction in spacetime, breaking this fundamental symmetry in a very subtle way, and in doing so, its energy could manifest as the driving force behind the accelerating expansion. One of the most developed frameworks for this idea is known as Einstein ether theory. In this model, the ether is not a substance but a field, represented by a vector that points in the direction of time at every point in space. This time-like vector field is woven into the fabric of general relativity itself, interacting with the gravitational field and altering the equations that govern the expansion of the universe. The presence of this field changes how gravity works on cosmological scales, and under the right conditions, it can naturally produce an accelerating expansion without the need for a cosmological constant or quintessence. It's a profound shift in thinking. The acceleration isn't caused by a mysterious energy. It's a consequence of the universe having a fundamental, albeit subtle, preferred direction in time. The beauty of this approach is that it is highly constrained and therefore testable. For Einstein ether theory to be viable, it must not contradict a century of precise experiments that have confirmed special relativity. The theory is designed so that its effects are incredibly faint in regions of strong gravity and high velocity, perfectly matching all existing solar system tests. Its unique signatures would only become apparent in the extreme gravitational environments of the very early universe or in the low-density, vast expanse of the cosmic void. For instance, the theory predicts subtle differences in the way gravitational waves propagate compared to standard general relativity, and it can affect the precise balance of elements forged in the Big Bang. As our observational tools become ever more precise, we may soon find evidence that the ether, in a sleek new form, has been with us all along, not as a medium for light, but as the hidden architecture shaping the destiny of the cosmos itself. This idea of rethinking gravity's fundamental nature leads us to one of its most mathematically daring revisions, the concept of non-local gravity. In Einstein's general relativity, gravity is a purely local force. This means the curvature of spacetime at any given point, and thus the gravitational force experienced there, is determined solely by the matter and energy present at that exact location. It's an instant point-by-point interaction. Non-local gravity proposes something far more radical and strange. It suggests that the gravitational force you feel right now isn't just determined by the objects immediately around you. It's influenced by the entire history and structure of the universe. The gravity here depends on the gravity everywhere else across vast distances and times, integrated together through immensely complex equations. The mathematics behind this involves what are called non-local operators, which are essentially integrals over all of spacetime. Instead of Einstein's field equations, which are local and differential, you get equations where the curvature at one point depends on an integral of the curvature over a large region, or even the entire past light cone. It's as if the fabric of spacetime has a form of memory or a far-reaching connectedness that we never anticipated. This might sound like it violates the principle of locality, a cornerstone of modern physics, but proponents argue it could be a necessary feature of a more complete theory of quantum gravity, where entanglement and other non-local phenomena already play a starring role. So how could this possibly explain the accelerating universe? The key insight is that these non-local terms in the gravitational equations don't just vanish in an empty universe. Even in a completely smooth, vacuum spacetime, these historical and global contributions to the curvature can persist. They can generate an effective repulsive force that is built directly into the modified laws of gravity themselves. In certain formulations, this non-local component behaves exactly like a cosmological constant, driving a late-time accelerated expansion. The stunning implication is that dark energy isn't a substance. It's a ghost in the machine of gravity, an emergent phenomenon arising from the universe's non-local memory of itself. We wouldn't need to add a mysterious new energy component because the acceleration is already encoded in the long-range correlations of the gravitational field. One of the most prominent examples of this approach is the Desir-Woodard model, which introduces a non-local term into the Einstein-Hilbert action involving the inverse of the D'Alembertian operator, a mathematical way of saying the equations incorporate information from an entire region of spacetime. This model was specifically constructed to generate cosmic acceleration without dark energy, and it can be tuned to match the observed expansion history of our universe. Other approaches seek to derive non-locality from more fundamental principles within quantum field theory, suggesting that the effective action for gravity might naturally contain these non-local pieces when you properly account for quantum corrections. However, this incredible theoretical promise is matched by immense challenges. The first is mathematical complexity. Non-local equations are notoriously difficult to solve and to even define properly, often requiring clever and subtle techniques to handle the integrals over the entire history of the universe. The second and more crucial challenge is observational testing. For a theory to be viable, it must not only reproduce the observed acceleration, but also pass all the other tests that general relativity has aced, from the precise orbits of planets in our solar system to the behavior of binary pulsars and the properties of gravitational waves. The fear is that introducing non-local terms might wildly disrupt these well-understood regimes. Initial studies show that with careful construction, some non-local models can indeed pass these local tests, but they often face a tougher challenge, reproducing the exact pattern of wrinkles we see in the cosmic microwave background. The precise peaks and troughs of this ancient light are a sensitive probe of the universe's expansion history and the growth of structure, and so far, the standard lambda CDM model with its dark energy fits this data exquisitely well. Any challenger, including non-local gravity, must meet this incredibly high bar, a task that continues to drive theoretical research and numerical simulation in this fascinating and ambitious corner of cosmology. Building on that profound idea of a universe as a cosmic projection, let's explore a specific and compelling application of the holographic principle to our accelerating expansion. This is the theory of holographic dark energy, a model that dares to assign a precise, concrete value to the energy density of the vacuum, based on nothing more than the fundamental limits of information. The core insight here is both elegant and staggering. In a holographic universe, the maximum amount of information you can pack into any region is not proportional to its volume, but to the surface area of its boundary. This means the energy density, the energy per unit volume, should be limited by what that bounding surface can describe. To turn this principle into a number, theorists proposed a simple but radical formula. They suggested that the energy density of dark energy should be proportional to the inverse square of the size of a specific cosmic boundary, the future event horizon of the universe. Think of this horizon not as a physical wall, but as the ultimate limit of what we will ever be able to see. It's the maximum distance that light will ever be able to travel to us in the infinite future, given the universe's accelerating expansion. The size of this horizon is constantly changing as the universe evolves. The theory then makes a breathtaking leap. It posits that the mysterious energy suffusing the vacuum is directly determined by this cosmic scale. A larger horizon means a larger information screen, which in this framework translates to a slightly lower energy density. This creates a dynamic and self-adjusting feedback loop that is far more sophisticated than a simple cosmological constant. In this model, dark energy isn't a static number plugged into Einstein's equations. It's an evolving quantity that responds to the very expansion it drives. If the acceleration were to increase too rapidly, the size of the future horizon would shrink, which according to the formula would actually cause the energy density to go up, counteracting the excessive acceleration. Conversely, if the expansion slowed, the horizon would grow, lowering the energy density and allowing the expansion to continue. It's a remarkably elegant and self-regulating system, a universe fine-tuning its own expansion through the holographic information limits of its own boundaries. The real test, of course, is whether this beautiful idea matches what we actually see when we look at the sky. The holographic dark energy model makes a specific prediction about the equation of state parameter, the W value that describes the pressure of dark energy. Unlike the cosmological constant, which has a fixed W of exactly -1, holographic dark energy predicts that W should evolve slightly over time. In the past, it should have been a little bit greater than -1, and it should be evolving to become a little bit less than -1 in the future. This is a distinct signature that astronomers can hunt for. Current observational data from supernova, the cosmic microwave background, and the large-scale distribution of galaxies provides a crucial check. The results are a fascinating mix of promise and tension. The data we have is precise enough to tell us that W is very, very close to -1 right now. For the holographic model to be correct, the deviation must be extremely subtle, lying just at the edge of what our current telescopes can detect. Some analyses of the data show a slight preference for this evolving behavior, a nudge that could be interpreted as a hint in favor of the holographic idea. However, other, more comprehensive studies find that the simplest version of the cosmological constant still provides the best overall fit. The model isn't ruled out, but it's being squeezed by increasingly precise measurements. Its greatest legacy may be in charting a path forward, demonstrating how deep principles from quantum gravity and information theory can be brought to bear on the greatest problem in cosmology, providing a testable alternative and reminding us that the most satisfying solution will likely be one that connects the very large to the very small. But what if we could tame the terrifying potential of phantom energy, smoothing out its catastrophic instabilities to create something stable and sustainable? This brings us to the ethereal and fascinating world of ghost condensates. Remember, phantom energy's core problem is its negative kinetic energy, a property that makes it want to spin out of control, leading to that universe-ending big rip. A ghost condensate is a special type of field that also possesses this seemingly bizarre negative kinetic energy, but with a crucial difference. It includes a higher-order stabilization term that prevents the runaway feedback loop. Imagine a car with an incredibly sensitive gas pedal that, if pushed too hard, would make the engine explode. Now, install a sophisticated governor on that engine, a regulatory system that allows the car to use that immense power but caps its maximum speed, ensuring it runs smoothly and safely. That's essentially what the stabilizing term does for a ghost condensate. It takes the raw, destructive potential of negative kinetic energy and channels it into a constant, stable state that can permeate the vacuum of space. The theoretical foundation for this lies in the powerful framework of effective field theory, which is essentially physics' way of saying, this works for now at these energy scales. It allows physicists to write down all possible terms in an equation that are consistent with the underlying symmetries of nature, even if we don't yet know the ultimate fundamental theory. The ghost condensate emerges naturally within this approach as one of those possible, self-consistent terms. It's not necessarily a fundamental field itself, but rather an effective description of how the universe might behave at very low energies and large distances, exactly the conditions where dark energy operates. This makes it a particularly compelling candidate because it doesn't require inventing entirely new physics from scratch. It operates within a well-established and pragmatic methodological framework, exploring the outer boundaries of what is mathematically and physically possible. Perhaps the most intriguing aspect of ghost condensates is their profound connection to the universe's very beginning, inflation. In many models, the ghost condensate can act as a form of late-time inflation. The early universe is thought to have undergone a period of incredibly rapid, exponential expansion driven by an inflated field. Once that field decayed, the inflationary period ended, and the universe settled into the more sedate expansion governed by radiation and matter. But a ghost condensate could, in theory, kickstart a new, much weaker phase of accelerated expansion billions of years later. It wouldn't be nearly as violent or rapid as the initial inflation, but it would be a sustained, gentle push, exactly what we observe today. This provides a beautiful, unifying symmetry, suggesting that the same fundamental physics that set the universe into motion at the beginning might also be responsible for its final fate, bookending cosmic history with two distinct but related periods of acceleration. While still a highly theoretical construct, the ghost condensate represents a brilliant attempt to wrestle the most unstable and dangerous ideas in cosmology into a stable, testable form, offering a potential pathway to understand dark energy without invoking a cosmic doomsday. Yet another profound idea emerges not from modifying gravity or adding new fields, but from reimagining the very first moments of the universe itself, all the way back to the Planck epoch. This is string gas cosmology, a bold alternative to the prevailing theory of cosmic inflation, and it offers a completely different origin story for the large-scale structure we see, one that might also provide a natural explanation for dark energy. To understand it, we have to venture into the realm of string theory, where the fundamental building blocks of reality are not point-like particles but tiny, vibrating loops of energy. Imagine the universe in its earliest incarnation, a hot, dense, and incredibly small space, seething with a chaotic gas of these vibrating strings. They aren't just floating passively, they are constantly interacting, colliding, winding around the compact dimensions predicted by string theory, and exchanging energy in a frenetic quantum dance. This initial state is the core of the theory. In the standard inflationary paradigm, a mysterious scalar field called the inflaton is responsible for driving a brief period of exponential expansion, smoothing out the universe and planting the seeds for galaxies. String gas cosmology proposes a different engine for this process, the thermodynamics of the string gas itself. The key lies in a special property of strings that point particles don't have. They can wrap around compact dimensions. These winding modes act like a source of tension or pressure that can actually resist the natural tendency of the universe to expand. In the very earliest, hottest moments, the universe is hypothesized to have been held in a state of quasi-stasis, almost frozen by the balance between the momentum modes of strings pushing for expansion and the winding modes holding it back. This prolonged, nearly static period is called the Hagedorn phase, and it's during this time that the strings have the opportunity to reach thermal equilibrium across the entire universe, naturally solving the horizon problem that inflation was designed to fix without requiring a period of superluminal expansion. Eventually, as the universe cools slightly, the winding modes begin to decay. This breaks the delicate balance, allowing the three dimensions of space we inhabit to begin expanding freely, while the other extra dimensions remain compactified. But here's where the connection to dark energy becomes truly fascinating. The expansion isn't driven by a false vacuum energy as in inflation. It's a natural outcome of the string gas thermodynamics. Furthermore, the model suggests that this initial gas of strings didn't just dictate the expansion. It also directly generated the initial density fluctuations that would later grow into galaxies and clusters. The seeds of structure are imprinted by the quantum fluctuations of the string gas itself, and the model makes a specific prediction. The primordial spectrum of fluctuations should be almost perfectly scale invariant, but with a tiny red tilt and a complete absence of primordial gravitational waves, a signature that is distinctly different from many inflationary models and is a key target. Future observational tests. So how does this all loop back to the mystery of dark energy? The connection lies in the leftover energy from this primordial string gas and the specific way the universe was born from it. Some versions of string gas cosmology propose that the vacuum energy we observe today, the cosmological constant, could be a relic of that initial state. It could be the faint, residual energy of those string vibrations that have been diluted over 14 billion years of expansion but never quite vanished. Alternatively, the process of compactifying the extra dimensions and stabilizing them, a major challenge in string theory known as moduli stabilization, could have left behind a small, positive energy density that is now manifesting as dark energy. The theory provides a framework where the acceleration isn't a late-time anomaly, but is subtly connected to the universe's very first moments, offering a potential, deeply unified narrative from the Big Bang to the present day. While still a developing and highly theoretical framework, string gas cosmology stands as a powerful testament to the creativity of modern physics, demonstrating that even our foundational stories of creation are still open for revision, and that the key to the universe's final fate might have been written in the vibrations of the very first strings. We have journeyed through theories that modify gravity, that introduce new fields, and that reimagine the very fabric of space-time. But perhaps the most mind-expanding solution of all is the one that asks us to consider not just our universe, but all possible universes. This is the final frontier of our exploration, the string theory landscape and the multiverse. To understand this, we need to venture into the heart of string theory, the leading candidate for a theory of quantum gravity. One of the most profound predictions of string theory is that it doesn't predict a single, unique universe with one set of laws. Instead, it suggests the existence of a vast landscape, a cosmic catalog of perhaps 10 to the 500 or more possible stable configurations for the vacuum of spacetime. Each of these configurations corresponds to a different universe with its own unique set of physical constants, its own laws of physics, and crucially, its own value for the cosmological constant or dark energy. Think of this landscape not as a physical place, but as an immense abstract terrain of possibilities. Each valley in this landscape represents a different stable vacuum state, a different possible way for a universe to be. Some valleys are deep and stable, representing universes that could last for billions of years. Others are shallow and metastable, representing universes that might collapse or decay almost instantly. The value of the dark energy density is just one of the many properties that varies from valley to valley. In this cosmic lottery, the number we have measured for our dark energy is simply the one that got drawn for our particular universe. It's not special, it's not fine-tuned by a deeper law. It's just a random selection from an unimaginably vast distribution of possibilities. This directly leads us back to the anthropic principle, but now with a concrete, physical mechanism behind it. In an infinite multiverse where every possible vacuum is realized, the vast majority of these universes are utterly sterile and lifeless. They might have a cosmological constant that is too large, causing them to rip apart before any structure can form, or too negative, causing them to recollapse immediately. Only in the exceedingly rare universes where the constants fall within a narrow window compatible with the existence of complex structures and observers can anyone be around to measure them. We find our universe's value for dark energy puzzlingly small, not because of a fundamental law, but because it is a prerequisite for our own existence. We could not find ourselves anywhere else. This idea, while philosophically jarring, is a direct consequence of the mathematics of string theory and the discovery of the vast number of ways to compactify its extra dimensions. It transforms the cosmological constant problem from a physics problem into a selection effect. The real question is no longer, why is dark energy this value? But why do we find ourselves in a universe that permits us to ask that question? Of course, the most common criticism of this multiverse explanation is that it seems to make the value of dark energy untestable and therefore unscientific. If we can't observe these other universes, how can we ever prove this is true? Proponents argue that the theory is indeed testable, but in a more subtle statistical way. The multiverse hypothesis makes a prediction that the value we observe, while seemingly improbable, should be typical of what observers would measure. We shouldn't expect the value to be zero or perfectly optimal. We should expect it to be just enough to allow galaxy and star formation, but not so small that it's unnecessarily fine-tuned. Our measured value of dark energy fits this prediction remarkably well. It is small enough to allow galaxies to form for billions of years, but large enough to now be dominating the cosmic expansion. Furthermore, if the multiverse is real, there might be other, more direct signatures. Some theories suggest that our universe might have collided with another bubble universe in the distant past, leaving a detectable imprint in the cosmic microwave background, a kind of cosmic bruise on the sky. While such a discovery would be monumental, the search so far has yielded no confirmed evidence. The string theory landscape and the multiverse it implies represent the ultimate scaling up of the dark energy problem. It is a solution that is both breathtaking in its scope and humbling in its implications. It suggests that the deepest laws of nature may not be unique and inevitable, but local and contingent. The answer to the mystery of our universe's missing energy might not be found in a beautiful equation that applies everywhere, but in the sobering realization that we live in one cosmos among a possibly infinite number, each with its own rules, its own history, and its own fate. It is a theory that doesn't provide a neat, mechanical explanation, but instead offers a profound shift in perspective on our place in the grand scheme of reality. From the elegant simplicity of Einstein's cosmological constant to the mind-bending possibilities of a holographic universe and the cosmic chameleon behavior of a dark fluid, our journey through these 30 theories reveals a truth just as profound as any single answer could be. The human drive to understand is boundless. We've explored the idea that empty space itself might be alive with quantum energy, that gravity itself might be an emergent illusion, and that our entire cosmos could be just one page in an infinite multiverse library. We've considered forces that change with their environment, particles that could be their own antiparticles, and the haunting possibility that the constants of nature might not be constant at all. Each idea, from Mundra right of galactic rules to the cosmic conversations of interacting dark energy, represents a different path up the same magnificent mountain, a unique blend of mathematical rigor and sheer creative courage. This incredible diversity of thought isn't a sign of confusion. It's the sound of science working at its absolute best. The fact that brilliant minds can look at the same data, the same distant supernova, the same cosmic microwave background, the same large-scale structure of the universe, and propose solutions that range from extra dimensions and tachyonic fields to ghost condensates and entropic gravity is a testament to the richness of the mystery itself. It shows that we are not yet at the end of physics, but perhaps at the very beginning of a new chapter, one that will require a revolution as profound as those sparked by relativity or quantum mechanics. The very existence of so many competing, compelling theories is a clear signal that we are digging at the very foundations of reality, and that the final answer, when it comes, will likely change everything we think we know. The quest to find the universe's missing energy is far more than a technical puzzle for cosmologists. It is one of the greatest detective stories ever told, a cosmic whodunit where the fate of everything hangs in the balance. Does our story end in a silent, frozen fade, a catastrophic rip, or perhaps something we haven't even dared to dream of yet? The investigation is ongoing, with new data pouring in from telescopes like Euclid and the Vera C. Rubin Observatory, and new theories emerging from the world's brightest minds. This isn't a mystery that will be solved by one person in one moment, but by a collective generation of curiosity, each observation and each idea bringing us incrementally closer to a revelation. And this is where the story truly includes you. The act of looking up and wondering, of engaging with these grand ideas, makes you a part of this ongoing discovery. So we want to hear from you. Which of these theories captured your imagination? Does the holographic principle bend your mind in the best way? Does the elegant desperation of the entropic principle feel like a profound insight or a clever cop-out? Do you think we need to find a new particle or rewrite our theory of gravity? Share your favorite cosmic contender in the comments below. We read every single